Hello, everyone, and welcome to another CIWEM event on the 9th of July. The topic this afternoon will be regarding reservoir safety and the Bewl Reservoir Drawdown project. My sort of fellow colleague within the South Eastern CIWEM branch, Christopher James, and his team will be presenting this afternoon on the project. But before they do, I just have to provide a little bit of housekeeping to you all. So just to make you all aware, the webinar will be recorded. With CIWEM, we do put up the webinars on the website. And there is a YouTube link that does take a little bit of time from this event to be uploaded. But with it, you will also find past digital events, which is great to see. If you do experience any technical issues and need any assistance, there is a raise your hand function within Zoom. Raise your hand, let us know what the problem is via chat, and then myself and another member of the team will be able to assist you. It is a sort of private chat function if you want it to be, or it can be into the main room. In addition to that, there will be an opportunity for questions at the end, which is great to see. And if you would like to put any questions to us, make a comment or use the Q&A facility on Zoom and type your questions in there. Obviously, with this only being 1 hour, there is a possibility that we might not be able to address every question, but we will seek to try and respond to all those questions we're not able to after the event, and we will select some of the questions as we go through. Finally, this is it does attribute to your 1 hour CPD, but there won't be a certificate. And obviously, the other bit to add is that with this being mainly a CIWEM event, we do recognise ICE and ICE support on this as well, which has been great to see. So thank you ever so much. Chris, I'm going to down my screen and hand over to you. So thank you very much.
Yes, thank you, Daniel. Hello, everybody. My name is Chris James. I am the project manager for the client side, so Southern Water. So essentially, my role has overseen the end-to-end delivery of the project, acting as the interface between Southern Water and our delivery partner, CMDP, ensuring, of course, that the project is delivered safely to the required cost, program, and quality standards. John, would you like to introduce yourself?
Hi everyone. I'm John Troke. I work for Stantec, and on the Bewl project, I was acting in the role of design technical lead. I'm a civil engineer and a dam engineer by background.
Thank you, John. Ian?
Yeah, good afternoon, everyone. I'm Ian Bentley. I'm the construction and delivery lead, so project manager from the contractors side for CMDP on the Bewl project. I joined the project early 2024, so partway through, but then saw it through the main construction phases to completion.
Brilliant. Thank you, Ian. Last but not least, Caroline.
Hi, everyone. I'm Caroline Dugard. I'm the Framework Environmental Manager at CMDP Plus, and I was involved in Bewl right from the beginning, all the way through construction, and now as it stands, we're just about to hand over.
Brilliant. Thank you, Caroline. So before we get into the exciting project details and technical engineering solutions, a little bit of a context here. So Bewl Reservoir was completed in 1976. We've actually just celebrated its 50th anniversary, and it's located on the Kent and East Sussex border near Lamberhurst. Now, what makes this body of water so special is that it's actually the largest body of water in southeast England. And for those of you that have been watching and enjoying the World Cup football, fun fact, it's actually got a surface area the same size as 436 Wembley football pitches. So it's humongous. It's, of course, a key source of drinking water for East Sussex and Kent, supplementing the drinking water network for hundreds of thousands of customers within Southern Water and also Southeast Water customers also. For example, the reservoir is the main feed for Burham Water Supply Works. In the summer, where it supplements the low River Medway. And Burham supplies over 65,000 customers just in West Medway. So it's absolutely huge. Now, so why is this reservoir project needed? Well, as I'm sure you can all appreciate, the greatest resilience risk for any impounding reservoir such as Bewl is structural failure. Now, while the probability of such an event is very, very low, the consequences are absolutely catastrophic. Now, of course, a stark reminder of this was Toddbrook Reservoir incident at Wadey Bridge in 2019. Now, following a period of intense rainfall, part of the spillway collapsed, raising concerns that the dam itself could fail. Thousands of residents were evacuated, emergency services were mobilised, and as you can see from the photos on your screen, the army was deployed to help stabilise the structure and prevent a potential disaster. Thankfully, of course, a breach was avoided. However, the incident clearly demonstrated the potential severe consequences of a reservoir failure, including risk to life, widespread community disruption, and significant economic damage. Now, managing this low likelihood but high consequence risk is therefore a fundamental responsibility for reservoir owners and operators such as Southern Water. Now, it's really important to note here that Toddbrook wasn't the catalyst for Bewl project. The requirement for emergency drawdown at Bewl had already been identified through the statutory reservoir process in 2018. Toddbrook simply occurred a year later and provided a real-world example of why these safety requirements are so important. Now, at Bewl, following the publication of updated DEFRA and Environment Agency drawdown guidance in 2017, a Section 10 inspection undertaken in 2018 concluded that the reservoir did not have sufficient emergency drawdown capacity. Now, the inspecting engineer therefore required a facility capable of lowering the reservoir's upper 5 meters within 5 days during a dam safety emergency. Now, a subsequent risk assessment at Bewl highlighted the scale and consequences during a credible worst-case dam failure scenario. Impacts were estimated to include risk to more than 300 lives and economic damage exceeding £900 million. Now, in response, of course, Southern Water, in partnership with CMDP+, developed and delivered a comprehensive solution to enhance Bewl Water's contingency drawdown capability. Now, the construction of this project started in 2023, and commissioning has only just recently completed in 2026. Now, here is the solution, enabling the reduction of the upper 5 meters of the reservoir within 5 days. As you can see on the right-hand side here, the marine pipelines, 3 huge siphons over the dam, facilitating that rapid controlled drawdown at 37 meters cubed per second. Now, I've been reliably informed that that's equivalent to around 1 Olympic-size swimming pool every 66 seconds. And again, I must add, this is in a safe, controlled manner. Now, this water then flows through the priming chamber via pipes where all the pumps are located, down the dry side pipes that you can see on the screen, into the discharge chamber, and then down the underground culverts into the spillway channel before entering the River Bewl. Now, this project is supported by piezometers and instrumentation within the Earth's embankment to monitor the internal dam conditions and detect changes affecting structural stability. So there's a bit of a context for you all on what the project is and why it's been delivered. I'm going to hand over to your good self now, John.
Thanks, Chris. Yeah. Okay. So firstly, before we settled on siphons as the preferred solution, there was a staged options selection process. We did start with a long list of options, but very quickly it became apparent that many of those options simply didn't have the capacity to discharge the amount of water that Chris has just been explaining, those large volumes, or other options weren't acceptable in terms of construction constraints in respect to reservoir safety. So, for example, any options that involved tunneling through or under the dam were very quickly discounted. So our long list of options very quickly got whittled down to just 2. Option 1 is the one you're seeing on the screen there. We call it valved inlets into the overflow tower. So the 3D image on the left, you're seeing the existing overflow shaft on the left and the existing draw-off tower on the right. So this proposal would be to put 4 large diameter openings into the overflow shaft. We estimated we probably need 1200 millimeter diameter pipes going into the overflow shaft, each with valves to open and release that water when required. So this was developed to a concept stage, but then eventually it was ruled out for reasons that I'll explain in more detail on a subsequent slide. But our other option was, of course, the siphons approach, which is shown on the next slide, Chris. So this is a view of the reservoir in blue. So it's a plan view of the dam, and you'll see the general proposal to provide 3 siphons up and over the dam in the location shown as those red lines, and then to convey the water from the siphons from the siphon discharge chamber via a buried culvert, which is shown in yellow there, to bring it to the existing spillway chute and away safely. So that was our option 2. Next slide, please, Chris. The image on the left shows the existing Bellmouth overflow shaft. You can see from that it's a relatively tall and slender structure. You'll also see that the shaft wall is quite thin. We also found another drawing that suggested that the steel reinforcement in that shaft wall was quite minimal. So we did some stability assessments, and we found that putting 4 large diameter holes halfway up that shaft was not really acceptable from a structural stability point of view, particularly with the weight of all the valves and the pipe work that would be installed along with the operating platforms or whatever would make it more top heavy. So the analysis suggested that from a structural stability aspect wasn't necessarily a feasible option. But there was also a second reason to discount it as well. As I mentioned, the openings would need to be about halfway up that. We decided it wasn't feasible to demolish holes in a structure like that using underwater technology. So we believed that there would be a need to temporarily drain the reservoir down to the level of those openings to do the construction. And that would have been quite an undertaking. The graph on the right, the blue line is kind of your average reservoir fluctuating levels. So these are the seasonal variations of Bewl in a normal year. And the red line is what we roughly thought we would have to do to those reservoir levels to build the overflow option, which would be to draw it down significantly, which just shifting the water out of there might take up to a year, and then to hold it at a low level before refilling it over quite a period of time. So that red line was deemed unacceptable from a water resources perspective. Conversely, the siphons option we consider could have been constructed generally around the normal reservoir operating regime. which is suggested by that green line there. So it's just a sort of formalization of the normal reservoir fluctuations with a degree of active management to ensure that those levels could be achieved in reality during the works. So for those reasons, siphons were selected as the preferred option, and we moved on to the definition and design phases. Next slide, Chris. So for definition, just going back to what Chris has already said, that we had a requirement to achieve 5 meter drawdown from full supply level within 5 days, and that's with a Q50 or a mean or median catchment inflows to the reservoir. It was important that the siphons could be primed and operated over that full operating range. So there was a need for them to be primed down to a level of full supply level minus 5 meters. And it was also required that the siphons should be wet tested routinely in the future. So notionally, one siphon being fully wet tested every 6 months. We consulted guidance from the Syria Siphons in Dams publication, and also for some previous case studies, particularly Queen Mary Reservoir from Thames Water. And those examples gave us a couple of key principles that we chose to adopt. We wanted a dual priming system. That's where you can fill the downstream section of the siphons simply by pumping water into the pipe and filling it until you fill the siphon up to the crest level. And then you use vacuum priming to prime the crest section and the upstream leg of the siphon. Going for a vacuum priming approach means that you don't need to have a submerged valve on the inlet to the upstream leg, and there's significant advantages for us in doing that at Bewl. Another principle we adopted early, rather than setting the siphons low so they could potentially self-prime, we opted instead to set them high above full supply level. By doing that, it meant there's no risk of accidentally priming them or any accidental release of water through the pipes, unless very deliberately by using the priming facilities. So by doing that, there's no need to have an isolation valve in the crest section of the siphons. Next slide. So I'll go through the design starting at the upstream end, heading downstream. So the first consideration is the siphon inlet. We needed to set the siphon inlet sufficiently below water to keep it submerged. So there's various standard equations for submergence. The idea is that you have it sufficiently submerged to avoid vortexing when it's operating. If you have vortexing going on, then that inlet could gulp in lots of air, and in a siphon system, those chunks of air could act to break the siphon effect and stop the flow. So it's very important to avoid air entrainment through the inlet. So we used our standard equations to pick a level, and then we tested it using computational fluid dynamics, CFD, which are the colorful images at the bottom. And they confirmed no vortexing and a fairly sort of tranquil approach into the inlets. But just to give some additional security on that, the drawing image on the right, which is a section, you'll see that the inlet bell mouth is surrounded by an inlet cage. We put the top of that cage is actually a solid steel plate to act as a hood, which also helps prevent vortexing at the inlet. Okay, next slide. The siphon pipeline structural design, if you like, we did that by producing a stress model, which is shown by the upper image. And us civil engineers who are used to designing below ground pipe work, if you work on a siphon scheme like this, you'll soon find that above ground pipe work is a completely different beast, and there's a lot more to think about in many respects. So we did this stress model, and we modeled a number of hydraulic scenarios to assess internal pressures in the siphon pipes. And we also modeled a number of external scenarios, which effectively gave us the environmental scenarios that gave us the external pressures on the pipe. Things like wave slam on the wet side, on the left there, the waves in the reservoir hitting against our pipe. But most significantly, thermal effects in summer and winter, which were quite onerous. So the drawing on the bottom there, that's a long section through the siphons with the inlet on the left. You'll see the siphons, the upstream leg of the siphons are sat on concrete pads placed onto the existing dam revetment, and those had steel saddles that were designed to slide to accommodate thermal movement. Similarly, on the right side, on the downstream slope of the dam, you'll see some concrete pads with some screw piles going down into the dam embankment, and those concrete pads were also fitted with sliding saddles to accommodate movement. And at the bottom of that downstream slope, there was also an expansion joint to take up movement before the horizontal section to the discharge chamber. Okay, next slide. Firstly, the priming chamber then. So this is in the crest of the dam. So we opted to provide a reinforced concrete chamber embedded into the downstream side of the crest of the dam. And the idea was that all the machinery, moving parts, controls, everything would be housed in that concrete box, so that it was an inherently safe structure. And by doing that, there was then no need to put up any unsightly security fencing on the crest of the dam, which wouldn't have been a good option. So, and by doing that, we were effectively able to turn the roof of that priming chamber into a publicly accessible viewing platform. The bits of hand railing you see around some of the covers there is actually demountable, so that wouldn't be there the majority of the time. So it's a safe structure for the public to go on top of, and without risk. So that's the priming chamber from the outside. We'll now go to the next slide. So this is the priming chamber with the concrete box removed so that you can see inside it. At the right side of that 3D image, you'll see 4 shapes with a person stood between 2 of them. That's basically the duty standby water priming pumps and the duty standby vacuum pumps, are what those 4 objects are there. The going for the dual priming system has the benefit that while you're vacuum priming one siphon, you can already start water priming the next one, so they overlap. That meant that we could prime all 3 siphons in well under 3 hours, so that in an emergency situation, you'd be confident of getting these siphons up and operating very quickly. And then also shown on the siphons, you'll see some various pipe work and valves that are there to aid that priming process and to allow the siphons to be broken if needed, to break the siphon effect and stop the flows at the end of a test, or if you've achieved what you need. Okay. Then at the downstream end of the siphon pipes, we've got the siphon discharge chamber. So here we opted to use Glenfield submerged discharge valves. The requirement to test the siphons that meant we had to minimize the volume of water released by each siphon test. So for that reason, we put hydraulic cylinder actuation on these valves so that they could be opened and closed within 70 seconds, which is remarkably quick. If you've ever sat around watching an electric actuated valve open and close, it can be quite a tiresome task, but these are much quicker. The design adopts a standard Glenfield valve civil arrangement as well. Each of their valves is housed in its own stilling basin with internal baffles for energy dissipation, and then the water wears out from each of those individual stilling basins into a common collection channel, from where it then gets conveyed by the culvert. It's worth noting that when we opted for the quick acting valves, we also did a surge analysis to make sure that action didn't create unacceptable pressures in the siphon pipes upstream. Next slide, please, Chris. From the discharge chamber, the water is conveyed by the culvert. It's a very large culvert, 4 meters wide, 2.5 meters high or deep. And because of the topography of the valley sides that the dam's situated in, it was laid on quite a steep gradient. So it's 140 meters long, sat on a 1 in 10 gradient. So that creates the potential for high velocities. There's some standard guidance and software available from America that we used for initial checks. We used software called HY8, and that told us that for this particular arrangement, we should be looking at internal dissipators spaced every 2.5 meters. And those were in the form of just 250 millimeter high weirs, effectively, to send the water sort of cascading down. And then at the downstream end, we simply flatten the culvert out and create what's called a USBR type 1 stilling basin, which is the simplest form of stilling basin, really. And that basically ensured that the water exited the culvert and joined the existing spillway chute in tranquil conditions with velocities in an acceptable range. Next slide. So we did the initial analysis, as I mentioned, using the software HY8, but then to be sure of ourselves, we also modeled it using CFD. So the image on the left shows the whole system coming from the discharge chamber at the top down the culvert to the existing spillway chute. This demonstrated that the flow in the culvert was generally free channel type flow over most of its length. So there was space between the water and the ceiling of the culvert. It showed that we were keeping velocities within the accepted range for these types of structures. And then by doing the downstream end where it entered the spillway chute, we were also able to show that the water entered the chute and turned to head out the way it needed to without excessive turbulence and out of channel flow. So it was a very useful exercise. The image on the right shows just the upstream end where the discharge chamber joins the culvert, and that showed us that the turbulence of the water wearing out from those submerged discharge valve stilling chambers and landing in the launder channel, that turbulence caused a constriction as the water entered the culvert. And so it did mean the culvert was surcharged for the first 20 or so meters while the flow effectively set up into the normal regime and straightened itself out and headed down freely. So we were aware that we had a surcharged culvert for the first 20 meters, but we had a robust structural design, and we were able to use the CFD to check positive and negative pressures. Sometimes you can get the water sort of up against the underside of the ceiling and then coming down and creating suction. But we were able to check the maximum positive and negative numbers, and it was well within the structural design, so that wasn't a problem. Next slide, please, Chris. This is a view of the downstream end of the works. So on the 3D image there, that's our culvert and stilling basin coming in from the right-hand side. See at the bottom, the lime green colour. That's a weir wall that we constructed across the downstream end of the existing spillway chute. So in this image, the water is coming towards us, and then it hits against that green wall. So that weir that we constructed is a retention weir. So that means that the water coming down the culvert from the siphons gets collected behind that weir, and then you'll see there's a number of openings in that so that the water can be released to it's a tiny water course downstream, that can be released very gradually. And then there was a bit of an operating platform, which is the blue just above the lime green there. In the back of the picture on the left, you'll see some blue pipe work. This was where we uprated a bottom outlet washout arrangement. So this is so that we could improve the drawdown characteristics below the operating range of the siphons to get the lower portion of the reservoir volume out quicker than in the current situation as well. Next slide, please, Chris. So this is my last slide. So this summarizes, I guess, what the scheme achieved. Those of you who are used to looking at drawdown studies will be familiar with these graphs, but they take a little bit of getting your head around. So on the left is the reservoir water, on the y-axis is reservoir water level. On the x-axis is the time in days. So the orange coloured line is what we had before the job was started. So that indicates to you it's very flat, and it basically goes off the right hand side of the chart, and it suggests that if we'd have done nothing, then it would have taken much more than 80 days to draw down the top 5 meters of Bewl Reservoir. The blue line is what we achieve with the siphon. So it has a very steep start where we draw down the first 5 meters in 5 days using the siphons. And then it flattens out considerably, but then we get the benefit of our uprated washout as well. So that shows us that we then get down to 25% of the volume of the reservoir in less than 50 days. So a very satisfactory result from those curves. And that's my part complete, I think, Chris.
Fantastic. Thanks for that, John. So I've got the challenge of trying to talk about the construction of this project within 10 minutes. So I'll do my best and do a whistle-stop tour through the construction of Bewl. So I think the best place to start is this photo, because it really sums up a lot of the unique things with Bewl. So one, we've got the engineering complexity of this, working on an existing dam. The scale of it, I'll talk about the size of the cranes that we're using in a second. The situation, the customer interface here. So the general public had access to the road that goes right down the center of the site there. So we had general public able to walk right through our site. And you'll see to the right-hand side, there's an aqua park just outside where our marine works were based. So again, the customer liaison and interface there was a particular challenge. And you'll also see that we're in beautiful green countryside. We're in the High Weald area of outstanding natural beauty, which Caroline will touch on a bit later. So what you can see here, I'll start talking through the construction process from upstream working down, and you'll see some of the structures that John's just been talking you through. So the compound area that you can see where there's a large green pipe on the land side, right in the center of the photo, this is where we were fabricating the pipes to then lift marine side. So these are 30-meter long sections of pipe that needed to go down into the reservoir. The largest sections we could get on a wagon shipped to UK was a 12-meter long section. So we had to weld on site the 3 sections together. So we had pipe rollers and a sort of mini factory on site to weld those up and then recoat them. This was during the lifting operation, lifting these pipes out into the reservoir. So these 3 sections welded together, like I said, 30 meters long, weighing approximately 29 tons. So the crane, you can see there is a 500-ton crawler crane with, I believe it's 260 ton of counterweight hanging off the back as a super lift. And as I said, while we were doing this operation, there were kids playing on the aqua park. And also gathered a lot of public interest. We had BBC and ITV news cameras watching us during one of our most challenging lifts on site. So the pipes for the marine side, as I said, were fabricated together on site, and then the ends capped off so that then when we lowered them into the reservoir, they floated. So if we go to the next slide, Chris, we then floated them and moved them along to where they needed to be on the dam crest. We could then attach some trolleys to them, and we had some quite specialist and bespoke temporary works for this operation. So you'll see on the picture on the left, there's a pipe floating in the reservoir there, and it's got 2 steel trolleys attached to it. So they're the steel frame structures that you can see touching the pipe. And the pipe itself was suspended between floating pontoons with these A-frames above them. So that enabled us to hold the pipe and then position it on the revetment where we wanted it. And we used some steels going down the revetment as guide rails. So those trolleys had wheels on them, they sat into those guide rails, and then from that position we could then winch them up into place. So if we go to the next slide, Chris. You can then see on the left the winching operation, and the challenges we had with this was trying to get the flange to clear the saddles that John had been talking about, and be able to pull up and position it exactly onto the other face, which is from the pipework that's cast in to the dam crest. So I'll discuss the alignment of that and the challenges we had with that. As John said, these saddles are also on a slip bearing, so we had to also think about how we restrained them, clamped them to the pipe carefully so that they were in the middle of their travel, so that they could get full benefit for that thermal expansion and contraction. So the bottom right shows those pipes installed at the end of the project onto the fixed bends. And if you go to the next slide, Chris, you'll see the alignment issues we were dealing with. So again, these were fixed pipes. The pipes going into the dam crest were cast into concrete. So we had to get the the gaskets and the mating face is absolutely perfect on these. Due to the pipes needing to hold a vacuum, so 0.9 bar G on them, we needed a very specialized gasket to be able to deal with those pressures, as well as being able to meet the design life, because these joints are not easily accessible, as you'll see the works we had to do just to get them into position. So that meant we had to go for a specialist material on those. With those materials, we didn't have as much give as you would usually do on, for example, an EPDM rubber gasket. So we've only got about 0.8 millimeters, which when you look at the size of these 1.7 meter diameter pipes, I've been reliably informed for calculations, 23 thousandths of a degree. So trying to get the alignment of these pipes coming up the reservoir and moving them in the saddles to get that alignment was definitely a challenge, but one that we overcame. We put flanges on loose on those bends and then welded them and then sent them off to be finished fabricated to ensure we could get that alignment on those. So next slide, Chris. So one of the challenges, and John mentioned this before about the previous profiles of where the water levels had been in the reservoir. So we were carefully monitoring this and we had to phase our works around where the water levels would naturally be in the reservoir. So the reservoir is a great resource. As Chris said, it provides water for many, many homes. And the majority of the water in the reservoir has been pumped into there. There's not a huge amount from catchment runoff into the reservoir. So there's been an investment in paying to pump it into the reservoir. And for water security, we obviously want to keep as much water in there as possible to make sure we've got it for not just this summer, but the coming summers afterwards. So we had to time our works and make sure we could deal with the predicted water levels. In typical fashion, the summers that we were working over were some of the driest we'd had on record and some of the driest for the last 10 years. So we were monitoring water levels 3 times a week, plotting where that was projected to go based on the previous data that we had from previous years, and we're planning our works accordingly to account for that. So on the left, you can see we were planning how much freeboard we had on lifting the pipes out. Obviously, as the water level goes down, it also goes away from the dam, hence us needing such a large crane to lift it out that far into the reservoir, but also for pipe install. So to have these pipes floating and be able to pull them up the reservoir, we needed enough water there so that we had enough freeboard for the pontoons to float. So yeah, those were 2 of the challenges. And then the final one was then also having enough water for commissioning. So as the water levels drop down, we then also need them to increase enough so that we had the required water level there. The next slide shows another one of the challenges that we had with water levels, which when we came to doing the landside works, excavating the dam crest. So as John said, we went for a siphon system that meant that these pipes could be quite high in the dam, but we still had to excavate through the clay core. That meant we had to time this carefully with when the water level was naturally low, but then complete the works in sufficient time so that Southern Water could pump into the reservoir and restore those water levels ahead of the oncoming summer. That meant we were quite time pressed for this, so we had to do some very careful planning and also careful protection works of the dam. This is when we're excavating into its clay core, so it's when it's at its most vulnerable. We wouldn't want that clay core deteriorating and potentially leading to catastrophic consequences. So we had to do careful monitoring of that, doing hand shear vane tests, and also protecting the core, so keeping it exposed for the minimum amount of time possible and putting temporary covers on it as well. So I'm pleased to say we managed to achieve that, and the photo below is the team stood on the dam crest just before Christmas 2024, which is our challenge of getting those works completed. So on to the next slide. So then this is the discharge chamber. So an aerial view of that gives a sense of the scale of it. If you went to Bewl now, and you'll see in a photo later, there's only 3 meters of this structure visible above ground, but the actual structure and excavation itself was 10 meters deep. The base slab itself is 1.8 meters thick with meter thick walls. So it's a substantial concrete structure with some complex structures in there as well. As John mentioned, the chamfered corners inside the individual cells were particularly challenging to construct. Next slide, Chris. This is the discharge culvert. So as John says, this was a buried culvert for 140 meters. And again, working on that relatively steep slope, trying to pour the concrete there and work with that, particularly with all the energy dissipators going down there, again, was challenging. We did an open cut excavation there, And now this culvert's got up to 5 meters of soil reinstated on top of it. So some significant landscaping works we had to do. So the next slide shows the inside of that culvert and those energy dissipators that John referred to. So casting those in, and the structure is a composite precast and in situ concrete structure. So the roof panels that you can see at the top were precast panels that we placed on top, and then had an in situ concrete topping slab and in situ concrete walls and base. The water you can see coming through there is because we had the hatch open. I assure you it's not leaky structure. You go on to the next slide, Chris. So yes, we had some challenging lifting operations. I mentioned earlier the 500-ton crane lifting the pipes out into the reservoir, but lifting these discharge valves into the discharge chamber was also quite a challenge. They're 9 meters high each, 21-ton valves, and yeah, had to be treated carefully. So we got them on the wagon from Scotland, had to stand them upright and then carefully lift them into the chamber, which didn't have much room around it when you consider the chamfered corners in there, and also access scaffold required to get to the bottom of the chamber to connect the holding down bolts when we place these into position. So some careful lift planning, and we used 4D visualizations on this to plan the lifts and also to run the lifting team through. So on the next slide is a good example of that. Hopefully the video will start playing. And this was one part of the works. We had to thread these pipes into the priming chamber. So in the very sped up video, we had to lift the pipes through and then re-sling them while they were suspended, so that we could pass them through underneath the concrete beams there. So the team did a really good job of this, but we spent a lot of time doing a load of planning on this. So we did 4D visualizations again to model how we would lift the units, where people would be positioned, consider all the health and safety impacts, as well as the slinging arrangements and how we would access each part. We then used this to brief the lifting team. So we showed them this a few weeks out, got their input on it, made sure they were fully aligned with the method that we were going for. And then we used it again as a daily briefing for them before we started the operation. We then used the footage that you're seeing now was recorded for the purposes of reviewing with the lifting team. So as part of a continuous improvement cycle, after each lift, we stopped with the team, got them back in, reviewed the footage together, compared that versus the 4D of how we were planning on doing it, and discussed there any optimizations, any things that didn't go according to plan, so that each one we progressively improved on. The one you've seen was the last one, and it was the windiest day. We were getting close to the limit on the crane for the wind there, but the guys did a really smooth job of installing that, and yeah, showed that the system we were using was really good and managed to make that smooth operation. So next slide, Chris. So as John mentioned, we also had some pipe work to do down the bottom of sites. This was upgrading the outlets, RO9, the reservoir outlet 9. So by comparison, this was relatively small and easy pipe work after you've been dealing with 1.7 meter diameter. The 800 stuff down the bottom was a lot smaller, but challenging nonetheless, dealing with the existing assets, excavations next to existing assets, and connecting into them and old pipes. And I'm sure people in construction will know the challenges that can come with that. But you can see on the right-hand side there the picture of when we tested that, to show that we've done the connection and successfully got the flows out that we required. On to the next slide. So as you'll see in the video on the right-hand side, this is what I believe John referred to as tranquil flow, coming out of the end of the culvert. And there's some significant work doing commissioning. We had a fantastic commissioning team doing this. This is the real life view on the left of what John showed you in the priming chamber. So the bright orange pumps there are the water priming pumps, and on the left-hand side are the vacuum priming pumps. So our team, commissioned all those systems with a remote operation MCC for these as well. And we successfully did the testing that you can see on the right-hand side. I believe that was one pipe operating at 50%. You can see there, so you can imagine what that culvert would be like if we had all three running full bore. On to the next slide. And that's the final works. So the grass seed's starting to take, all of our work's completed on site. And as Chris said, we just commissioned earlier this year and got our sign off that we'd met all of the requirements of the Section 10. And the QC signed that off and sent that to the EA earlier on. So I'll hand over to Caroline to talk about the environmental impacts.
Thanks, Ian. Yeah, if I can have the next slide, please, Chris. Yeah, so this is just the environmental setting of it, really. As you've seen in quite a few of the other pictures, we're nestled right there next to the Reservoir Dam. We've got the main river, which starts after the existing spillway and heads up north. That's the River Bewl. The thick pink line is the Southern Water ownership boundary. Of course, we've got some ancient woodland bound on the boundaries of that. And as Ian said, we've got the Bewl Water facilities going on as well. So lots of things happening there. I'd just like to also point out the Sussex border path, which goes along the dam crest. So, of course, we had to divert that and deal with that during construction. There's also the grazing land to the north of our site and a spring rising in the middle of that land as well. So I'll talk about why that's significant in a little bit. If I could have the next slide. So in the enabling phase, of course, we're located in that high weald national landscape. So for the designation often referred to as the area of outstanding natural beauty. And that was, we weren't subject to any planning permission for the works. We were subject to EIA screening. So the land was viewed as Southern Water operational land, and only certain elements of the works were subject to planning. So the project as a whole was EIA screened to see if it would need a full EIA for the assessment of impact onto the environment. So during that EIA screening, we went through a lot of different aspects of the environment. So first of all, visual aspect, of course, we're changing quite a large area of just greenery next to that dam wall into operational gubbinses, I suppose I would say. And so in that option selection, that they talked about with the engineering selections, we've also looking at reducing that impact and going for those below ground pipeline areas where practical and possible, and then using the existing assets as well. There was a high weald colour study. You can see the picture there. We had those 3 different greens, and I think even though that picture is an active construction site, you can see how well that green kind of merges into the landscape. And I think once everything has grown up and sort of bedded in, I think it will be a good merge of colours in that area. So that's one thing that we had to talk to the local authority about some depth. Then there was the water and the flooding issues. So, of course, it's the use of the existing spillway to retain the water during the test events, and installation of the weir and the penstock at the end of the spillway and the stilling basin, allowing those test waters to be stored and then gradually released into the downstream river at the required rate. And then the existing and new ground profiles were considered as part of design as well. So the buried culvert and the spillway, and then the reinstatement and enhancement measures all kind of helped to put us into the landscape and not have too much of an impact, above ground and visually. And then the human amenity, I mentioned the permissive path. Again, that was incorporated into the design and into the construction methods and program as well. So ensuring access to the top of that reservoir has been maintained. And then ecology, we did do some vegetation removal, but we looked then at habitat reinstatement and enhancement measures as well as part of that enabling. So we gave a lot of commitments to how we were going to lessen the impact to the environment whilst we did it, and for permanent installation. So if I can have the next slide, please. So whilst we were in delivery, that EIA screening opinion, everything that we put into that, so the designs, all of the commitments that we made were our rules on site to stick to. So we also had quite a lot of water management challenges. So you've seen in quite a few of the images that the guys have put up already, how much of a sort of a hillside we were working in and what the actual kind of topography and environment was. We've got weald and clay there. We've got an awful lot of runoff that comes from any rain event. So when we started to do our excavations. So if you could click, Chris, and bring up that next image, you can see the difference between these two images. Of course, we've got a lot more area of our site open. We've got excavations for the discharge chamber, for the priming chamber, and for the culvert itself, all kind of open at the same time. We've got stockpiles. So it's a huge challenge then to have rain events, you know, very extreme rain events in some circumstances, pushing water onto our site. So there was a huge amount of challenges in that way. And then on the wet side, so the marine side, I guess, we had zebra mussels to contend with. They're present in the environment there. So lots of controls to make sure that we're not spreading those off-site with any equipment, boats, etc., that we've got on our as part of our construction methods. And we had a silk curtain in place for the works as well. So preventing anything that's in our sort of working wet envelope from entering further into the reservoir. If I could have the next slide, please, Chris. So we had a lot of stakeholder interactions, not only for the path, but for the whole job. We wanted to make sure that whilst, you know, people couldn't object to a planning permission, people could, you know, very much see us when we were on site, and we were, you know, very much under the microscope. So we had an extensive stakeholder interaction program. And then the picture that's on screen now is our habitat enhancement sort of commitment. We took some plantation trees away. We, of course, took quite a lot of the grassland away to do our construction. And so we had vegetation removal at certain phases, but then we wanted to enhance that. So we looked at the ecologist, a great botanist and a great ecologist, looked at the site as a whole and saw that we could enhance different habitats in the landscape already. So there was wet woodland already down alongside the River Bewl, but it was fragmented. It's in little pockets, and it could really do with species enhancement and area enhancement. So we've done a wet woodland creation with some black poplar trees. We've got a picture of those in a moment. There we go. There they are. So these are really rare trees in Kent and East Sussex. There's only around 20 adults of them in the whole region. And we were given by the Black Poplar Trust, part of the High Weald Association, we were given 20 in the first year and another 20 in the second year, and a vast majority of those have survived down in that area. So it's really good news, and hopefully they will go on to mature to adulthood. And then we've also done some meadow creation. So where we have taken the grassland away, we've added to the we've taken high weald seed mix that's been specially collected within the area and sown those seeds as well. The other picture on the screen actually is us planting around those black poplars. So it's been enhanced with around 2,400 other wet woodland species trees. So they're all the holes being prepped for it, and it looks really, really good at the moment. We also diverted part of the spring. So we knew that the spring did used to trickle down to this area, and we reinstated that route. It had been blocked up for sheep grazing, etc. But we put that back in place, and we've actually created much more of a wet woodland than it would have been before. So it's working really, really well, and it's looking really good. And even in the drought at the moment, it looks really wet. So that's really good news. And then the last thing to talk about is the boggy hollow creation. So boggy hollows are these dips in the clay. They hold the water a little bit more on the hillside. They create a different landscape in a little ecosystem that attracts different plants and different insects and supports a different kind of biodiversity there. So our botanist found that small water pepper, which again has no kind of records in the southeast in this kind of area in the last kind of 25 years. So that small water pepper is thriving in these little boggy hollows, And so we have created more boggy hollows for that to have, you know, more chance of reproduction and to enhance that habitat as well. So it's been a very exciting project, both engineering wise and environmentally. And that's it from me.
Thank you so much to all of the speakers, particularly in this extreme heat. Yeah, let's have a look at any questions. Again, if we don't have the opportunity to answer all of the questions, we will be able to write up the questions and responses within the next couple of weeks. So if I stop sharing, Daniel, are you happy to read out a couple of questions?
Yeah, I'm happy to read out a few, but yeah, no, thank you ever so much, Chris, and to your wider team. That was a fantastic webinar, really insightful, covered all areas, the construction, the planning, the environment side of things. So yeah, really insightful. And thank you all for your time this afternoon. A couple of questions I do have, conscious of time as well. Let's see what we've got here. We've got one quite big one, but it's quite important. What provision mitigation plan did the project team have in place to manage water levels and inflow to satisfy the QCE during construction of pipework, especially working through the dam core and removal of the wall? Did you have any issues during this critical element of the project, and what downstream environmental impacts are there when testing on a rolling 6-monthly basis?
So I think I could probably
covers a few areas. So yeah.
Yeah, I could best take this one, so I'll try and get stuck in. So yeah, we discussed the works with the QCE, obviously, as we were planning and working forward. So we worked with him to have a designated freeboard that we needed below the lowest level that we were excavated to and where the water levels were allowed to be. From memory, it was approximately 1.6 meters. And that was calculated based on John might be able to correct me here, I think it was a 1 in 100-year storm event, and the flows and increase in water levels that you would get in the reservoir in that sort of worst case scenario. We were obviously doing water level monitoring, while we were doing the excavation. We were doing that daily as well to see where those levels were going. So we had those mitigations in place. Did we have any issues when we were excavating the priming chamber? We were doing the monitoring. We did notice some deterioration of the clay core there, so we consulted with the QCE and backfilled around that. But again, the monitoring that we had in place was good that we picked that up, and were able to mitigate before that became anything more significant. The downstream impacts from testing are very limited, hence got the weir wall in there that was mentioned. So that weir wall is designed so that we capture the flow from the 6-monthly testing when you're just testing one siphon at a time, and all of that water can be retained in the existing stilling basin. And we then have penstocks there that we can slowly release it at a rate of 50 litres a second or so that we can minimise the impact to the flowing of the River Bewl further down.
We've probably just got time, unfortunately, just given the time for one more question. It's come from how close was the submergence results from the formula calculation, the CFD output? Were you able to use the CFD to understand any additional beneficial effects from the upstream hood?
Good questions. I think the answer's broadly no. The equations we used told us that it had to be at least 9 meters below full supply level. So we built that model and incorporated that into CFD and tested that one scenario, and it showed it was acceptable. We didn't then go on an exercise of fine tuning and lifting the pipe and reducing submergence to find out when it would break. We stuck with that. And similarly, the hood wasn't included in the CFD model, so it was added as additional benefit, but the benefit couldn't be quantified. But because we had the big cage structure, the cost of changing an upstream, a sort of lid that's a grill, and changing that to a steel solid plate wasn't a huge expense. So it was just a belt and braces really, and additional security.
But no, I think,
Thanks,
Chris,
John.
I'll hand back over to you quickly, but yeah.
Yeah, thank you. And again, fantastic speakers, and thanks for feeding in your expertise, and to the support team as well. As I said, we'll work together over the next coming weeks to provide responses to the other questions. But yeah, special thanks to everyone, including, of course, the attendees for braving the extreme heat. And yeah, I hope you have a wonderful lunch.
Yeah.
Thank you, everyone.
Thanks ever so much, everyone. And then just final one from me on CIWEM. If you enjoyed the event today, there are links in the chat for future events and other sessions and events that we have within CIWEM. So yeah, we'll look forward to welcoming you back in the future. And again, thank you to the panel and the presenters today. Very good, really informative and very enjoyable. Thanks ever so much, everyone. Take care. Bye-bye.
Thank you. Bye-bye.
Thank you.
Bye-bye.